Hi, sir.
Hello, Amy. How are you doing?
I'm very well, thank you. How about you?
Good, thank you. Okay, so we'll talk about binomial theorem today.
hmm
Last time we discussed about Pascal's triangle. Did you understand all that?
yeah, it's very clear.
Okay.
So, yeah.
Could you do some questions from your book on that topic?
Yeah, so far, yeah, which I've done, I've got it.
Okay. Any difficulties?
No, not
That's
yet.
right. Okay, that's right. So we had a long session on Pascal's triangle. Did you kind of understand all that?
Mm.
Because we are going to have
Most,
another long session on binomial theorem,
all right.
which will be about an hour long. So are you ready for that?
Yeah, I am.
Okay, great.
Let's do it.
Let's do it. So let me share the screen with you. We'll begin with the concepts. So here, you see my screen, right? Binomial theorem, concepts and examples.
Yeah.
Well, today in the class, we will actually discuss about how do we expand binomials and how is it related with the Pascal's triangle. We looked into this last time also. I hope you remember that. But we'll learn a technique of multiplying the coefficients that will make things simpler. Just as, Amy, do you remember synthetic division when we did polynomials? It is
Yeah.
simpler than long division. So you could have multiplication of coefficients to multiply binomials.
Oh.
Well, yeah, so that's very interesting. And then
hmm
we'll see patterns in binomials. We'll also go through this notation. You know, when we begin with binomial, there are so many terms which come into play. For example, I've written the formula for binomial expansion here. A plus b to the power of n is sigma, where r goes from 0 to n, and this symbol is n choose r. We also say NCR. That gives you the coefficient for the binomial terms. So n choose r, a to the power of n minus r times b to the power of r. Now we'll try to understand what is this sigma notation and also how to evaluate NCR. Well, the formulas are given here itself. We have given that sigma expansion. Sigma is a short form of writing the whole series, right? So series is, addition or subtraction of the sequence elements. So here you can see this particular expansion of a plus b to the power of n, and all this expansion is written in the short form with the sigma notation. So that's the beauty. The n choose r, which is also read as NCR. We say n choose r most of the time. I will say NCR in my lesson today.
hmm
So the NCR value can be evaluated by calculating this expression, which is n factorial divided by n minus r factorial times r factorial. Now, a factorial term may be new for some of our students. N factorial really means n times n minus 1 times n minus 2 up to 1. So all natural numbers up to n, when you multiply them, you get n factorial. So this is another short way of writing that long product, okay? So that is what it is. So these notations we'll again look into in short and then move on. Well, we have many examples based on binomial theorem, but here are a few very interesting and important ones. How do we approximate the value of higher powers? Let's say if I have 0.99 to the power of, let's say, 100, how do we figure this out? We can do it with binomial expansion. We'll also prove whether some expression is divisible by a number or not, or by an expression or not. And then we'll pick up many questions from extended exam previous questions, which will help you to do all the exercise and also get ready with your own exam, okay?
hmm
So let's begin with the binomial expansion itself. Anything to the power of 0 is always
1.
1, and a plus b to the power of 0 is also 1, nothing new about it. Then a plus b to the power of 1 is that itself, which is a plus b, right? Now we
hmm
get into the powers of 2. You know what a plus b whole square is, Amy? What is a plus b whole square?
A squared plus 2ab plus b squared.
Perfect, and that's what I've written. And what is a plus b whole cube?
I mean, it's written there. But
A cube plus 3a square
yeah.
b plus 3ab square and b cube. You
Hmm.
kind of know this formula. You may not be, remembering it at present. But what is a plus b to the power of 4? For sure, nobody knows this, right?
No.
So you might know a plus b whole cube, but a plus b to the power of 4 is not really known to student normally. Correct. Okay, so now what to do at this stage? Well, one thing could be if I have to calculate a plus b to the power of 4, I can multiply a plus b whole cube by a plus b. Definitely, I'll get 8 plus b to the power of 4, correct?
Right.
That is going to take some time, and here is how I will do it. So a plus b whole cube times a plus b, expand first a plus b whole cube, then multiply by a plus b. So 4 terms there and 2 terms there will give you these 8 terms. You can combine the like terms to give you the answer, which will be, since it is a power of 4, you will notice there are 5 terms in this expansion. So that is the normal way we will be doing it. However, the Pascal's triangle really help us. See here, we know what a plus b whole square is, a square plus 2ab plus b square. Now here, do you see the numbers 1, 2 and 1?
Hmm.
These are the coefficients for a plus b whole square. Do you see that? The next one is a plus b whole cube, and the next row is 1, 3, 3, 1. As you can see, 1, 3, 3, 1 is the coefficient in the binomial expansion. Similarly, what is a plus b to the power of 4? We get the terms coefficient as 1, 4, 6, 4, 1. And you notice that 1, 4, 6, 4, 1. It exactly matches.
Hmm.
So now you don't have to do all this, right? You straight away read the values from the Pascal's triangle and you can easily expand. Not just a plus b to the power of 4 or 5, any you can do, right? So now if
Right.
you have to do a plus b to the power of 5, what you need to do is just read the elements in this row and they become the coefficients, correct?
Hmm.
So that is how you do it, right? So from the binomial triangle, they are directly related. Now you can count the number of rows for fifth. It is row number, not talking about the Pascal's way of counting, but
Hmm.
otherwise if there is a triangle, we say this is 1, 2, 3, 4, 5, and this is my sixth row in this particular triangle. So you will notice that the correspondence of a plus b to the power of n is with n plus 1th row in the Pascal's triangle. Right? So this is very important thing to note, that if you have a Pascal's triangle, in that case, a plus b to the power of n, just count the number of rows. The n plus 1th row will give you all the elements which are corresponding to the coefficients. And this number here really helps. So that particular diagonal in the Pascal's triangle, which Pascal's triangle's version is diagonal 1, but here
Hmm.
it is the second diagonal. So that second diagonal will have that number, which is the exponent n. So, for a plus b to the power of 5, you see 5 there in the second place, right? So
All right.
that is
Yeah.
how you can remember, and very easily, even without counting, know which particular row to follow to get the coefficients for a plus b to the power of n. Isn't that cool?
Yeah. So all you need to do is go to the second diagonal and find the n, like the
Yes.
exponent n, and then got it. Okay,
Match
cool.
the end. That is true. That's
Yeah.
another way of doing it. Perfect. Now, we had been talking about coefficients and this multiplication. Always, it may not be, possible for you to get into the Pascal's triangle, and sometimes you may have to multiply the coefficients, right?
Right.
So generally,
Yeah.
so let's talk about that also. And here is a simpler technique to do this multiplication. We took up this example, a plus b to the power of 4 is a plus b whole cube times a plus b. And we know a plus b whole cube is a cube plus a, 3a square b plus 3ab square plus b cube. We can multiply by a plus b, and we got the result. I just copied the result from there, which is a to the power of 4, 4a cube b, 6a square b plus 4ab cube plus b cube. Now, here is how we do this multiplication. See, I made a kind of a table. I've written a plus b whole cube is these 4 terms, and a plus b is a plus b. Now, simple multiplication, if you want to do here, how will you do it? Well, first, let's multiply by b, correct? Let's multiply by b, And as we multiply by b all the terms, I'm writing them here in my row. So this is product by b, right? So b times b cube is b to the power of 4, b times the second term is written there, and so on. We get these 4 terms. And now we can multiply each and every term with a. And when you do that, you can write that here in that particular second row, correct? As you do normal multiplication. A is in the 10th place, right? So you may write 0 here and then continue writing. And then when you add that up, you get your result, which matches with your coefficients right there, correct? Now here is how, since you see that is the coefficients which are getting multiplied. So why to write all the terms like a square, b, ab square, and b cube? We could just write the numbers. So the idea here, Emmy, is that a plus b whole cube, we read that the coefficients are 1, 3, 3, 1. And in the coefficients of a and b is just 1 and 1, like 11, right? So let's multiply this by 11. 1, 3, 3, 1, multiply by 11. Well, simple as that. When you multiply by 11, you get 1331 and 13310, correct? Because that is how you do multiplication with 11. Perfect. Add them up. When you add them up, you get 14641, which exactly matches with your result.
Oh, that's so cool.
Yeah. So simply put the coefficients multiplied by 11. That also gives you a hint. Most of the time, when we have something like a plus b times something else, and you're expanding a plus b to the power of n, all the coefficients will have this pattern of 11, right? It will be kind of 11 to the power of n. Do you see that? Since we are multiplying by 11, you get the idea.
Wait, so 11 to the power of n. So let's say we want to find... Oh, wait, I don't get 11 to the power of n. So I understood why you multiplied it by 11, but I don't get why it's to the power of n.
Correct. So when you multiply anything by 11, you get 11 times that thing, right? So many times. Get it? So each coefficient is being multiplied by 11. So 11 is a common factor. So most of the results will be multipliers of 11.
Yeah.
Correct? But there is a trick to this. You see the terms inside. We will show you this multiplication also in short. So just wait for a minute. Let's go through a plus b to the power of 5 first, right? So let's practice this particular method of multiplication, Amy. We know what a plus b to the power of 4 is. The coefficients are 1, 4, 6, 4, 1, correct? We just got it. Now, we want to find the coefficients for a plus b to the power of 5. We need to multiply by 11 because a and b have coefficients of 1 and 1 each, correct?
Right.
So multiplying by 11 is copy the whole numbers and then shift and copy, correct? You could do either way. So I have the numbers 1, 4, 6, 4, 1. I shifted them 1, 4, 6, 4, 1 with a 0 placeholder and then added them all. So when I add them, I get my coefficients as 1, 5, 10, 10, 5, 1.
Which is the coefficients for anything to the power of 5.
Do you see that?
Oh.
Do you see? So you don't have to bother about combining the like terms, bringing them together, and if by mistake you have picked out one of the powers, which really happens with me many times, then everything is wrong. But here, so simple.
So what you're saying is, if it's whatever to the power of n it is, you just minus 1 from that power, and then find the coefficients of that thing, and then multiply by 11, and then you get your coefficients of the term n.
Correct. Now there is a catch. When you add 6 and 4, you have to write the number 10, not 0 and 1. It's not the normal addition, okay? Because we are getting the whole coefficient at that particular position, or that term number. So that is the difference in writing 11 to the power of n and this particular number, right? So if you analyze, let's take it as an exercise. What is 11 to the power of 5? Write it down. And then write it in this particular fashion, right? If you have a term like 10, then 11 to the power of 10 will put 1 on the top and 0 here, right? And add 1 to the next column, correct?
Makes sense, yeah.
Right. So you can actually figure it out that it corresponds to that. And why am I telling you this? because you don't even have to get the coefficient of the previous term. Just 11 to the power of 5 will directly give you the answer. So let this be an
Really?
exercise for you. Yeah.
Wait. So let me quickly do 11 to the power of 5.
Yes, what? Tell me.
I got 161051.
161051, correct? Now look here. Let me write down. So 51 is matching, correct?
Yeah.
Now 0, think like this. This 1 should have been here, correct? Because 10, right? The numbers are
Yeah.
then that becomes 0. Do you see that? So this 0, but we cannot have a 0 here as a coefficient, can we? No.
No.
So we have to pull out 1 from here. So we get 10 here, and this becomes 5. So we have 5 and 1.
Oh my God.
Do you see the manipulation which you have done? So don't carry forward that 1. Bring it back. And then see your result. You get the coefficients.
That's crazy.
You can do 11 to the power of 8, 7, whatever. Because multiplication
Yeah.
11 is so simple.
What?
Right? So
I'm actually shocked.
So all the coefficients will work with 11. You get your result so fast. And that is how you have to do your addition. Be careful that all the coefficients, they actually increase up to the middle value and then they decrease. There is a symmetry. Perfect. So one after the other, we have an increasing number till we reach the center. And then once you reach the center, break off, copy the other numbers on the other side, right?
You always start from the left to the, like if you do it, the 11 to the power of n method.
Yeah, either way you could do. Yeah, this is better. Right side is better. Because we are used to working with the right side. Do you see that?
Yeah.
So right side is better. So you could do, when you're working with 11, you have 12 terms. 12 terms really means there are 2 terms in the center. So once we go through this chapter, you will understand all those concepts and you will be able to apply it very easily, for sure.
All right,
But this is a neat trick which you can actually adopt, okay?
All right, okay.
Now, next is, let's talk about these conventions, right? And the patterns which you observe in binomial expansions. So in short, we saw that a plus b to the power of n could be written with the sigma notation NCR a to the power of n minus r times b to the power of r. And expanded form is right there where NCR or n choose r are the coefficients which you can pick from the Pascal's triangle or you get it by multiplication. Now let's observe some things from the binomial expansion itself. First and foremost, this n is the degree, right? So the degree of the polynomial in the expansion remains as n only, right?
Yeah.
The number of terms in the expansion are how many? If n is the degree, the number of terms are n plus 1. The sum of the exponents of each term, like these are the terms, right? The sum of the exponents of these terms is always n, right? Coefficient terms equidistant from beginning or or end are equal. That means to say NCR is equals to NC n minus r. So from both the sides, you will end up at the same number, right? That is the symmetry. Now, the terms in the expansion of a minus b to the power of n, when I make b minus, then all those terms where b is with odd power will become negative, correct?
Yeah.
Therefore, we are going to get alternately positive and negative numbers, terms, symmetry. Coefficients, same distance away from the two ends are equal. So I've just repeated this. Well, that's what we wrote earlier. The coefficients are exactly the numbers in the Pascal's triangle. And as you said, look into the second diagonal and then you know the correspondence. This is the one row which is required, correct?
Yeah.
Now, as an exercise, what you could do is, here we have example 2. We just made a negative exponent. So you need to expand a minus b to the power of 6. You could use Pascal's triangle or your any other method to do it, right? At present, use Pascal's triangle to expand a minus b to the power of 6. Remember, b has to be taken as negative, and that will result in wherever you have a negative degree of b as a negative term. And clearly you can see that we have alternating negative terms as was mentioned earlier. Is that clear?
Yeah.
Perfect. Now, let us also learn a method of calculating the coefficients, because every time you just can't go back to the Pascal's triangle, nor can you make a Pascal's triangle with 20 rows, right? We
Right.
had one with 8 rows, and that is like too much. So there should be a way of calculating. Of course, there is. How do we evaluate binomial coefficient and choose R? Well, there is a formula, n factorial divided by n minus r factorial times r factorial. Well, this formula can always be applied. But here, I'm going to share with you a shortcut method of immediately calculating NCR without so many factorials in the formula, okay? So let
Yeah.
us evaluate what is 11 choose 4 or 11C4. Now, from the formula, we know 11C4, 11 factorial divided by 11 minus 4 factorial, that is n minus r, times 4 factorial. Perfect. Now, 11 minus 4 is 7, so we get 11 factorial divided by 7 factorial and 4 factorial. Now, what is 11 factorial? 11 factorial is 11 times 10 times 9, 8, 7, 6, 5, 4, 3, 2, 1. And 7 factorial, 7, 6, 5, 4, 3, 2, 1. And 4 factorial, 4, 3, 2, 1. So those are your factorials. You will notice that they cancel. Do you see this? Once you cancel them, what remains is 11, 10, 9, 8 divided by 4, 3, 2, 1. And then you can calculate this value easily, correct?
Oh, right.
What you notice here is, since we are working with number 4, we have 4 factorial in the denominator, and 11, 10, 9, 8 are 4 terms. Do you see that?
Yeah.
So there are 4 terms in both numerator and denominator. Do you see that?
Oh, so would it
Increasing from 11, 11, 10, 9, 8.
it would always be like that, right?
Yes.
So if you had, let's say, something 11 choose 3, you would have 3 terms on the
Yeah,
numerator.
3 terms, correct.
Ah, okay, got it.
That gives you an idea. If I do 11 choose 4,
Yeah.
the previous one you multiply by 3 over 1, correct?
Yeah.
So you will correlate so many relations. It's a very beautiful chapter. Now, example 4, as you said, 10 choose 4, right? I took a very simple number to work with. Since it is 10 choose 4, the numerator should be 10, 9, 8, 7. Multiply them together, correct? 4 terms. And denominator is 1, 2, 3, 4. You can reverse the order. There's no need to write always 4, 3, 2, 1. If you want, you can write 1, 2, 3, 4. It is the same product. Now you can simplify it very easily, canceling the terms, right? You can cancel 4 times 2 is 8, and 3 times 3 is 9, and 21 times 10, you get 210 as your answer.
Okay.
It becomes such a simple calculation. Do you see that?
You don't even need the calculator.
So this may be scary, but it's not that bad once you understand how to calculate, correct?
Yeah.
Good. So
do you think that's the best method to find the binomial coefficients?
Yes.
So not the 11 to the power of n method.
It reduces to the same thing, correct?
But which one's like, I understand this one more.
Yeah.
This one makes sense.
This is better. Whenever applied, this is better.
Okay.
And we'll actually, in the next unit, we will learn how to work with the coefficients and the binomial terms. And there we will get into details of working with these numbers, okay?
All right, okay.
But now we'll focus more on expanding binomials today, okay? We'll take different kinds of examples. These are few notations which I thought are very important to look into before we jump in some examples, right? So once again, I'm sharing with you this screen on notations, right? So just to recap, now can you tell me, sigma notation for writing binomial, this is, right? Sigma of this, where r, this value r, is between 0 and n. It is between them, including them, okay? It is not beyond 0 to n. And whenever we are doing binomial expansions, we are always working instead of natural numbers, right? So I should say whole numbers, correct? So it is discrete numbers, correct?
Discrete numbers.
Yeah. So it is not a continuous function. You can say sometimes we treat this under discrete functions also, correct? And always remember that the value of r is between 0 to n, both included. Perfect. And you know how to choose and all this, So that's fine. We can skip it now. Perfect. Now here is an example for you, Amy. Can you please read the question and then try to answer?
So example 5, binomial coefficient. Find the coefficient of each of the following in the given binomial expansion.
Yes.
A to the power of 4 times b to the power of 8 in a plus b to the power of 12.
Correct. So what will be the term which will have this in it, in the expansion?
Okay, so so n equals 12. So
Okay.
we'll have, if we're doing in the
NCR. Yes.
Like format,
Yes.
we would have 12, and then we would have to choose, looking at the formula below, we would have to find b. That would be the number, the number of b would be the one, r.
R is the exponent of b, right?
Yeah.
So remember, r is the exponent of b, the second term, and then you get 12, choose 8 as your coefficient. Do you see how simple it is now?
Oh, yeah,
Correct.
yeah.
So the expansion actually tells you exactly what numbers we are looking for within that huge list, right?
Oh.
So we know now 12, choose 8. And how will you calculate 12, choose 8? Tell me.
So what we just learned by doing, so do 12 to 5 because that's 8 terms, and then just do 8 factorial.
And then you can simplify and calculate easily. Perfect. Now, in the second example, we have p to the power of 5 and the binomial expansion of 1 minus p to the power of 11. Now, in this case, which term will have, what is the coefficient of the term which has p to the power of 5? Can you tell me this?
Which coefficient?
Yes.
R equals 5.
Yes, r equals to 5.
And n equals 11.
So simple. Now you have to write the term also. It is important to write the term. First is 1, right? So 1 to the power of 6, right? Which is 11 minus 5 and minus p to the power of 5, right? Because that is what we want, p to the power of 5. But remember, in your binomial, p is not p, p is minus p. And therefore, you have to put minus p here. Do you see that?
Yeah.
So sometimes we may miss it and make a mistake, but don't, right? So minus p to the power of odd exponent will give you a negative number. And of course, we get 11c5 as the coefficient, but with a negative sign, right? And calculation is easy. 11, 10, 9, 8, 7, multiply that, divide by 1, 2, 3, 4, 5. Done. Got it? Simple.
Yeah. Okay.
Got it. Now do this one. X to the power of 4, y to the power of 12 in 2x minus y to the power of 16. What will be the coefficient?
So n equals 16, r equals 12.
Perfect.
Then you take minus y to the power of 12.
Correct.
So, and then multiplied by 2x to the power of 4, because 12 plus 4 is 16.
Correct. Or 16 minus 12 is 4. Either way. This means 16 minus 4 is 12. But it is important to write both the terms. And that makes huge difference. Because see, 2 to the power of 4 becomes a part of exponent for x to the power of 4 y 12. You see that? And therefore, apart from 16c12, we have to multiply by 2 to the power of 4 to get the exponent, coefficient of this particular term. Do you see that?
Right, yeah.
Therefore, it is important to write the term and do not write the coefficient directly. I know it becomes very easy. You could always say that, but most of the time in examination, you'll get a wrong answer. Okay?
Okay, yeah.
Perfect. And this is just a quick reminder of what this binomial coefficient is.
Just one thing. With the last question, so 16 choose 12. Do you do that first and then do you multiply by 16, 2 to the power of 4?
2 to the power 4, yes, you could do that.
Just use calculator.
Yes, of course.
Okay, cool.
Sometimes, there will be 2 test papers, one with calculator, one without calculator. When the bigger numbers are involved, they will give
calculator.
you. Yeah.
Right.
So here is the next example for you. Now here we have alternate negative values. Write the expansion for 2x minus 3y to the power of 4, right? So in this case, we are going to use the Pascal's triangle to write the expansion of this particular term. So, Amy, can you tell me a quick way of writing the expansion of such an expression?
So since I know, because you said use the Pascal's triangle, since I
Yes.
know a plus b to the power of 4 is like obviously the expansion using the triangle, so a to the 4 like that. All I need to do is write that equation out, and then because I got a plus b, I'll just sub in a as 2x and then b is minus 3y, and then.
Correct. So you begin with this second diagonal of yours, look for the number 4, and then you know the coefficients 1, 4, 6, 4, 1. And so you have these coefficients 1, 4, 6, 4, 1, perfect. And you know the a and b's will come together and their power should always add up to 4 in particular order. A's power will decrease from 4 to 0, and b's power will increase from 0 to 4. And you get all the terms in between. Yes, you rightly said a equals to 2x, b equals to minus 3y. Replace your a and b with those values and then simplify and get your answer. That is how you'll do it. So we're done with this kind of question where we have 2x minus 3y, not simple a and b, right? Another question here is question number 7, which is we need to find the product with expansion. So sometimes they don't say same terms, right? There are two different binomials. As you have in this particular case, we need to multiply 1 plus 2x with 1 minus 3x whole cube. So you have to, expand it. Perfect. So in that case, you will have to first do the cube part, which is kind of difficult, right? So I've done it separately. It is better to do them separately. So 1 minus 3x cubed, you can always get to this particular row in the Pascal's triangle, which is the fourth row, which has 1, 3, 3, 1, and then use the terms 1 and minus 3x to expand and simplify. Once you have the simplified version, you can actually put this instead of 1 minus 3x whole cube, and then apply the distributive property multiplying by 1 plus 2x, correct? And then again, expand and simplify to get the result. So if there are two different kind of terms, you may have to apply the distributive property and expand as we have done in this particular example. Is that clear?
Okay. Yeah. So do you say that like with the 1 minus 3x to the whole cubed, the fastest and most efficient way is using Pascal's triangle and subbing the values back in?
Yes.
Okay.
Yes. So if there are no restrictions and the numbers are lower than, let's say, 8 or 9, Pascal's triangle is right before you, right? You can easily make it also sometimes.
Right.
Or you can write down NCR, right? General value, and also expand. It takes though some time with NCR.
Yeah, I was going to say.
Yes, it takes time with NCR. Now here, we need to explore something. So Amy, can you read what is this to explore?
So write the coefficient of x cubed in 1 plus 2x multiplied by 1 minus 3x whole cubed.
So tell me, what is the coefficient of x cubed in this product which we just calculated?
What's the coefficient of x cubed?
Yeah, so it's very small print.
Oh, 27.
27. Now, this question I'm asking you for a purpose. There could be a question which does not involve multiplication, but the question is only to find the coefficient of x cubed. You get my idea, right? In that case, what you could do here is, when you expand 1 minus 3x cubed, then how do you get x cubed? We are multiplying by 1 plus 2x, correct? We are multiplying by that. So in that case, you need to only check product of 1 and minus 2x cubed. That will give you x cubed, correct? Also, you could multiply 2x with 27x squared. That will also give you x cubed.
Yeah.
But only these two multiplications will give you x cubed. So the only thing which you should do in such a question in that case is When you multiply 1 with minus 27x squared, you get minus 27x cubed, right? And then when you multiply with 2x, 27, you get plus 54x cubed, right? And then add them up, and you get 27x cubed, and your answer is 27. You need not do the complete expansion. You get my point. So I need not do up to this stage. I will only work for these two and get my answer.
That's how you save time.
That saves time, and that is the way to do it. Because I could have given you 1 minus 3x to the power of 7, right? And then just ask for what is the coefficient of x cubed. Why will I calculate the terms after x to the power of 4? No need. I will only go up to x cubed, right?
Yeah.
And then I will multiply and get my answer. So I will do a partial expansion. So this partial expansion is a great technique of saving time and getting the right answer, especially when the question is only to find the coefficient of a product.
Oh, okay.
But the idea...
So, yeah, so it's the partial expansion only the first 2 lines then?
Yeah, because
okay.
you are interested in x cube, right? So
yeah.
if I have higher powers, I will neglect them. If I want x to the power of 4, why should I go there? I'm not interested. Correct?
Yeah,
go
perfect.
to the x cube and leave the rest. Then it
Makes
becomes very
sense.
simple. And you can use n choose r to calculate 2 or 3 values. It doesn't take time. Knowing fully well that NCN and NC0 is 1. So that
that's true.
And NC0 and NCN is 1, and NC1 and NCR minus 1 is n itself. So at least 2 you know directly, right?
Yeah,
so
that's true.
Not a big deal. Now, we'll get into examples which are there seen in examinations. We have different kinds of functions, right? We could have square root, we could have reciprocal functions. So in this particular case, in example 8, we will expand x minus 1 over x to the power of 5. So I just changed the type of function, taken reciprocal with a negative sign, just to give you a variety of, working with these terms in expanding them. So what we notice here is we'll definitely go with the Pascal's sixth row, fifth power, 1, 5, 10, 10, 5. And so and we know these terms also. So we'll write 1, 5, 10, 10, 5, 1, correct? And then we know first power is to the power of 5, and we'll get all those terms. So while writing the terms, take care that the second term is minus 1 over x to the power, 1 over x, right? Minus 1 over x. So you expect alternate positive and negative signs as shown here in your result. So remember that part. And you can simplify and get the result as shown here, no problems. Now, Amy, the question for you. Can you read this question and answer?
Explore. Write the coefficient of terms with even power in x minus 1 over x to the power of 5.
Yes.
So even power.
Yeah.
Oh wait, okay, so even power.
Even power is like 0, 2, 4, 6, 8, 10.
Yeah, so...
No, can't find it, right?
No, that's 1.
There is no term. I mean, there is no term. Don't worry. Don't try to find it.
Don't do that. That was a trick question. Yes. I was literally like, why can't I find it? Oh, yes. Okay.
So look into the situation. If we have an odd exponent, like in this particular case, and we have x multiplied by 1 over x, it's reciprocal. Those reciprocal terms with the even power will cancel away. I mean, when you add or subtract things, they will cancel away. So you'll have none of them. So if that is the question, there is a straight answer. None, 0, right?
So with reciprocal functions,
like x times 1 over x, yeah.
Yeah, if it's an odd to an odd power, there are no even powers because they cancel out.
No even big.
Oh, so that's like
so
a
experiment. What happens with it is even power. Okay. Now this. Why am I giving you these explore questions here? It's like a tape, right? When you're in the examination, these questions can save a lot of time. And if you get some multiple choice questions in some other examination, like in GCSE, you don't have. But
Yeah.
the examination, it can save a lot of time. Okay, tips.
Mm-hmm. Oh, I'm just trying to like write it out in a way that I can understand it. So in reciprocal
Yeah,
like
right on, right on.
values, the even powers cancel out. No,
Yeah,
if the
yeah,
okay.
even powers cancel out when we have odd exponent.
Oh, that's the word. Okay, even powers cancel out when we have even. Okay, got it. Thank you.
Next one I've taken with radicals, right? It is very difficult to work with radicals whenever higher powers are involved. So these surds you have to be really good at. And definitely you can expect a question in examination where you can have something like this. Square root of x minus 2 over square root of x to the power of 4. I've kept it simple. Simple
Yeah.
power, even power 4. Many terms will become, will get rid of the square root function itself, right? So you get polynomials, many terms. But how? It is very complicated. The whole idea of taking this right now here is to give you a practice chance. You could actually change the power to 6 or 7 and then try some questions so that you are conversant by adding these surds. Do you understand? Working with these exponents. Is that okay? Rational exponents.
Yeah.
So
Looks super complicated.
they are complicated. So
Yeah.
practice with them. That's the whole idea. And now in this particular case, you need to explore or write the coefficients of terms independent of x. Now, what does it mean? Terms independent of x means what?
Does it mean where like it's not with x? It's
Yeah,
like 24.
yeah, you are right. So like
Oh, okay.
24, x to the power of 0. So when they really cancel away x to the power of 0, right? So
All
we get
right.
a constant, and that constant is 24. Perfect. Now in the
Mm-hmm.
type of equation, if I write even powers here, this will be considered as even power. I mean, do you understand? 0 is an even power. So just
Oh,
yes. Okay.
how come?
0 is even. We consider 0 as an even number, right?
Oh
10
yeah,
is
because
an
it's
even number.
0 to
02468. Okay, remember that. So that is what. Question number 10. So these slides which are in different color kind of warning that be careful when you answer, and they are actually giving you some tips for your examination practice. So Amy, can you read this example number 10?
yeah. Application to approximate powers. Find an approximate value of 0.99 to the power of 5, correct to 3 significant figures.
Correct. Now it is not easy to do such questions, and many times even finding powers may become very difficult. Now, how we can use binomial expansion to do this? See a beautiful way. Not 99 as you said can be written as 1 minus 0.01. 1 minus 0.01. So now we have split it into two terms. We got a binomial to the power of 5.
Right. Oh, that's actually impressive. Okay. Yeah.
Now you can expand, and 0.01 is 1 over 100, correct? 1 over 100.
Mm-hmm.
One more thing. That 1 over 100 is your b term, right? Whose powers are expanding as we going to b to the power of 5. Now, as you move, like power of 4 and 5, 1 over 100 is going to be a very small value. So,
Oh yeah, yeah.
approximation really means neglect them. They're very small values, neglect them.
Oh, so it's just like it being 0.
Yeah, like 0. So
Oh,
you
okay.
need to just work with the first 3 values to get your answer. You get my
Oh,
idea?
yeah.
So 1 minus 1 over 100 to the power of 5, just work with 3 values, get your answer. So easy.
Whoa, that's so cool. Because if you look at that question from like a start, like how do you do 0.99 to the power of 5? Like that's
Correct.
crazy. How would you do that? But
Correct.
simply like that's like the key to unlock the problem, like splitting it into 2, 1
Yes.
minus 0.01. Because
Yes.
without that, there is
That's the
no.
key.
Yeah. My God, that's good. Okay.
And then division by hundreds and 0 multiples, 10
Yeah.
to the power of minus. So easy, correct? So you get those decimal numbers, add them up and get your value.
That's so cool.
Of
Okay.
course, it is negative, so alternating positive and negative, remember that.
Yeah.
And then you get your value. Do you see that answer? Correct?
Mm-hmm.
So the tip here is that whenever you have to evaluate some number like this, try to split it in a way so that binomial expansion can be applied. And if the second term is much, much smaller, then higher terms can be neglected. Got it?
Okay. Yeah. Got it.
Perfect. Example 11. Now here again, we are splitting and see how beautifully we are doing. And this is again a very good question. We will teach you how can we figure out about divisibility in polynomials, okay? And also you can find many of my videos on divisibility by numbers. I haven't taken one example here in this particular section, but you could always check that, okay? Prove that a to the power of n minus b to the power of n is divisible by a minus n. We need to prove it. Well, there are many ways to prove it. You know, you can do by method of induction also. There are so many other ways. And let us see how using binomial expansion we can prove it. See the beauty. A to the power of n I wrote as what? Can you read this? What is a to the power of n written as?
So you've written in brackets a minus b in brackets add b, whole thing to the power of n.
I got a binomial. A minus b is one term and plus b is the other term. You know, minus b plus b, they cancel away, right? It is just a. Do you see that? A to the power of n.
Yeah, but how did you? Whoa. Wait, how did you get a minus b? Why did you sub it in for
So a, I wrote a as a minus b plus b. It is a, right?
Oh, yeah, you need okay.
Then I
Right.
this as one term. A minus b is one term. So I got a binomial. I got two terms, binomial. Do you understand?
Yeah.
This is the power n. So I made this as a power of n. Do you see that?
Yeah.
Now I can expand like a binomial expansion. I got a binomial term. One is not a, but a minus b. The other one is b. So I expand this using binomial theorem. Do you see that? The last term is what? The last term is NCN b to the power of n. Of course, n is the power. The last term will be b to the power of n, correct?
Yeah.
NCN is 1. So basically, the last term is b to the power of n. I brought this now back to this side, left side, with a negative sign. A to the power of n minus b to the power of n. And look here, all of the terms have a minus b in them. So I can factor this out, and that becomes a product of a minus b. And therefore, I can say that a to the power of n minus b to the power of n is divisible by a minus b.
Yeah. It's that little, like, that first step, like that rearranging and doing that part. Like, it's similar to the other one, obviously, just a bit more, obviously, with letters and things, but still, same concept.
These are advanced level questions, Amy. So
yeah, I can tell.
At the end, you know, the last few questions,
yeah,
they're the killers. And if you know these tricks easily, they will write, what is 6 to the power of 2n minus 1 is divisible by some number. Do you understand?
right, yeah.
And
then I'll know this is the method to apply.
This is the method to do it. Okay? This is
Okay.
divisible by 35. Answer.
Yeah.
This is a real question, okay? 6 to the power of 2n minus 1 is divisible by 35. That is
then you have to be like, is it or is it not?
Yes. It is, and you prove that it is using this.
Yeah.
Okay, follow this. Now, another important thing here is sometimes you get these radicals to work with. They say, well, find the value of this times this, kind of like this, right? But always, you know, you have seen in GCSE, how do they do? They'll give a question, part A, B, C, D, and so on. So we have a question right from there, and is a plus b to the power of 4 minus a to the power a minus b to the power of 4. Evaluate this first. So part A is to find the value, an expression, I should say, for a plus b to the power of 4 minus a minus b to the power of 4. Correct? So we have alternating terms what will happen to them? We have even an odd term, some will cancel, some will double up, right? Once
Yeah.
you get that expression, then evaluate this. Then evaluate this means substitute A as square root 3, B as square root 2, and then find your answer. So that is how a question is designed for you, okay? And here is what we will do. When we begin with the first term, we know that half of the terms are going to cancel away, and those half of the terms, which because it is minus a minus b. So when you have a minus b, then it means that the second term is with negative, right? Fourth term is with negative, correct? Those alternating terms are negative. First is positive, correct? But when
Yeah.
it's minus, then in that case, negatives becomes positive. So the
Positive.
even number of terms double up. So here we have even alternate terms will double up. Even alternate terms are with NC1, NC3 and all. Not that number is odd. Do you see that?
Yeah, yeah.
So they double up. So this expansion basically is 2 times NC1 a to the power of n minus 1b plus NC3. As soon as you write NC3, you know what the other two terms should be, right?
Right.
A to the
Yeah.
power of n minus 3, b to the power of 3, and so on. So that becomes your series. Perfect?
Yeah.
Right. Now, you can actually, because we know n is 4, substitute 4 here, 4c1 and 4c3. The coefficient is 4, right? 4c1 is 4, 4c3 is also 4. Plug in 4 here in your expression, and you get a simplified expression, which is 8ab, a square plus b square.
Yeah, yeah.
A lot of algebra to be done, so have a good look at it. So basically, NC1 is 4C1 in our case, since we are working with the exponent of 4, right? And 4C1 is just 4, correct? 4C1 is just 4, right?
4C1 is just 4. Yeah.
Yeah, because only one number you have to write, 1 times and 4 times. Do you see that?
Yeah.
So 4 will be 4 times 3
4.
and 1 times 2. Do you see how easy it is to work? So don't think much about it.
Oh, okay. Yeah.
Correct. So, because this is our first lesson on this, you get 4 and 4 there, and you can combine and write 8ab a square plus b square. So that is the simplified form of this particular expression. And now a square, b square are there, and ab is there. Substitute with square root 3 and square root 2, simplify and get your answer, which will be, in this case, 40 square root 6. Okay?
Yeah.
Now, your question could be, they will say, evaluate this. They rather give this value as a square root 6. Find a. So you'll say a is 40. Get my idea?
Oh, okay. Yeah.
So that is how they will kind of give you a question, right? Something like this. Anyway, so we work with doubling up even terms. We'll take another example. Now this time what we have done is, just to give you a variety, similar question, I just changed the sign to plus, nothing more, right?
All right.
When
Okay.
I do that, in that case, I'm adding up the odd terms. Do you see that? So odd alternate terms will double up. Rest is almost the same thing, the formula. Square root 2 plus 1 to the power of 6 minus square root 2. So a for you now is square root 2, b is 1. Substitute, simplify your answer, and get the value. Is that clear?
Yeah.
Difficult question, but very important from test point of view.
Yeah.
Just a variety, very important variety, okay? Question number 14 seems to be very difficult. It is how to expand a trinomial. Well, we did see how to expand trinomials, correct? We made binomial as trinomial.
Yeah.
We'll do the reverse now. Of course, when you have to club 2. Now, if I have to expand 1 plus x square whole cube, what should you club? You should club these, right?
Oh, yeah. Because they're like the similar.
One separate. One is easy number to work with, right? 1 to the power of 3, 2, 1 is just 1.
That's true, yeah.
Club these two and keep the one separate, right? And so we say let y equals to x plus x squared, and so this trinomial becomes 1 plus y whole cube. I have to examples, Amy, because we don't want to complicate. What 3 is 1, 3, 3, 1, correct? So you straight away write down 1, 3, 3, 1 and expand. Once you do that, you get the term with y. You have to write y as x plus x squared and redo this work. second time, correct?
Okay.
Whenever
Yeah.
you have trinomial, you have to do twice this multiplication, correct?
Mhm.
And then simplify and get your answer. So in this case, that is our answer for this particular expansion, correct?
That makes sense. Yeah. Hmm.
Expected degree should be 6, 3 times 2, which is the case. So that is a small check. Clear?
Okay. Yeah.
Next question here is another type of examination question which says, connect coefficient of the terms. Now, we have done this many times as an explorer. Do you see that? I was talking to you about explore. What is the...
Oh yeah.
Can you
Yeah.
now read and answer this question, Amy? You're prepared for it.
Okay.
Yeah.
So in the expansion for x plus y to the power of 17, there is a term x to the power of k, y to the power of 9.
Yes.
Determine the value of k.
Yeah.
Oh, okay. So 17 minus 9 is 8. So k is 8.
Good.
Okay.
Next part.
Determine the coefficient of x to the power of k and y to the power of 9.
Correct.
Okay, so n equals 17, r equals 9.
Yes,
And
because
then,
you know 8 is there, right? You already know 8, and you know n is 8 plus 9, which is 17, right? Or you already know 17. No, you don't directly.
yeah, I just took it from the
You took it
question.
from there. You're smart.
Yeah, nice and simple. And then
Get your
we
answer.
work from there. So you just do like what you
Calculator.
said. Yeah.
You
Oh,
use
calculator.
calculator for this. Get your answer. Perfect. That's good job. So next is then a different type of a question which you can see in examination. Example 16. Polynomial and binomial applications. In the expansion of 1 plus x to the power of n, the first three terms are 1 minus 18 plus 144. Determine the value of x and n. That's the question for you, right? So let us see how to do such a question. So we need to find both x and n, but we are given the first three terms this time, okay? So now, without thinking much, first we can straight away expand, and that is what we know. We need to figure out, well, how do we correlate? First term is 1, and we know first term in this particular expansion, 1 plus x to the power of n, will be 1. So that doesn't give us much information. That 1 and 1 is fine. Perfect? For
Yeah.
the second term, we are given as minus 18. Now, second term here is what? nc1, 1 to the power of n minus 1, x. Well, that gives us a lot of information. And that means it is nx, right? nc1 means n, right? nc1 is equals to n. So we replace with n, and that is, so we get nx. So from here, we get our first equation, which is nx equals to minus 18. Do you see that?
Oh, yeah.
Because this term is nx, right? Now,
Yeah.
so
I
from
see.
here, you can write x in terms of n as whatever, and then look into the second term. The second term is given to you as
As nx squared? No.
144 here, and nc2, right? So nc2, 1 will be 1, x squared. So the nc2 x squared is 144. You get your second equation. Perfect. You have two equations, two unknowns. Unknowns are x and n. You can do elimination or substitution to get your answer. So what I've done here is nc2 is what? nc2 is n times n minus 1. You will prefer that, right? N times n minus 1, correct? Divided by 2 times 1, correct? You'll go direct.
All right. That makes sense. Yeah.
Makes sense? And
Yeah.
x squared. So x I replaced with this value. X squared means square of this, correct?
Yeah.
18 minus n whole square, which is 324 over n squared, right?
Yeah.
We are given that this is equal to 144. So we have equation in n, and from here we can calculate the value of n by cross multiplication. You get a linear equation here, and you can solve this to find the value of n. It comes out to be 9. Once you get 9, then you can substitute in your first equation and find the value of x also, which comes out to be minus 2 in this particular case. Is that clear to you?
Yeah.
Right? So In this particular case, the answer is 1 minus x value is minus 2, right? And this value is, sorry. So x value is minus, yeah, substitute minus 2 here for x, and to the power of n will give you these terms in the binomial expansion. Okay,
Yeah.
so that is how we particularly answer all these questions. There are 2 more questions to go, Amy. Now here we'll try to prove an identity. Now we are working with the coefficients. I'll actually look into this type of examples in our next lesson, but this is just to prepare you for that.
Okay.
Prove the identity that sigma r equals to 0 to n for NCR, 4 to the power of r is 5 to the power of n. It looks very tricky here. How do we do it? But there is a very important thing, as we did in the last case, 1 plus x, you saw 1 minus x that time.
Yeah.
If I have 1 plus x to the power of n, then all these powers are 1, right? The first term.
Yeah.
And what we get is an equation as a polynomial in x. Do you see that? NC0, NC1x, NC2x squared, NC3, and then NCnx to the power of n, correct?
Because 1 to the power of anything is just 1.
1, right. So you
Okay.
get increasing power of x. So you get increasing power of x.
Ah, okay.
That's what you get with NCR, correct? Okay. So that is what you get. In short, you can always write it like this. Now, since we want what is 4 to the power of r, what we have done here is we replaced x with 4.
Oh, so you just sub it in.
Yeah, just sub it in. That is my general formula. 1 plus 4 is 5, and 5 to the power of n is the expression which we wanted to prove. Do you see that? We just proved it.
Oh. Yeah, that got proved without my knowledge.
Yeah, without even, yeah, that is so true. It just came automatically.
Yeah.
Such a simple question. So if you write the general formula as such, and in that, we know it's the number is 4 we are looking for. Okay, put x as 4, right? So we get our result, correct?
Just one quick thing.
Yes.
Where did you get the 1 plus x to the power of n from the question? Did you just know it, or?
Oh, okay. So that's a good thing. So we started with 1 plus x to the power of n. That's, you can say, a tip.
Ah.
That's a great question. So where did you get 1 plus x to the power?
Yeah. We're not all really smart like you, sir. We need to know where it came from.
It came. That is so true, right? So we observe that there is only a difference of 1 here. Why not try it out, right? So we just tried it out. Now here is some question for you to explore. Can you answer this question? Read. Explore what?
Okay. Evaluate the sum of coefficients.
Yeah.
So NC0 plus NC.
Up to NCN. What is the sum of this series? Can you tell me?
What is the sum of these series?
N? So the hint is, if I expand 1 plus x to the power of n, the only problem is x. We don't want x. We don't have any x here, right?
Yeah.
So put x equals to 1. So if I put 1 here, I get 1 plus 1 to the power of n, which is 2 to the
power of n. Oh. My God, okay. Yeah. I keep thinking that, it's enough, like that's the stopping point. But then you keep pushing and you're like, there's so much more to know.
Yes. So we'll look into this series sum. Very interesting now, right? So just working with 1 plus x to the power of n, we can get sum of all the coefficients. And if we change a bit, we can get sum of squares, sum of negative, so many other ways, right? So it is a chapter in itself. So we'll look into that in more details later. Now here, another examination style question for you, Amy. Can you please read the question and answer?
So show that 1.01 times a million?
Yeah, maybe.
The power of a million.
A million,
yeah.
Yes.
Is greater than 10,000.
Yes.
Estimate the approximate value of 1.01 to the power of a million.
Yes.
or yeah, I was gonna say split it into two. I was actually gonna say that because it's like that 0.99 to the power of 5 equals
Perfect.
2. Yeah.
So this question could be asked in two different ways. As I said, you could estimate the value of this particular expression, or you may prove that this is greater than 10,000, right? So, and you just got it. We have to write this, split it into two, write it as a binomial, and we have 1 plus not point, not 1. And now we have an exponent. We'll just do the first three terms. Forget about the rest. Forget about that million, right?
Yeah.
Leave it aside. Just do the first three terms, right? So when you do the first three terms, the first term is 1. The second term is actually 10,000. And even leave the other terms because we just want to prove there's
Yeah.
10,000, right? We got 1
That's
plus 10,000 as a result. And so other terms are positive. So it is greater. We have done our job. Do you see that?
Yeah, it's so cool that because the higher the let's say n gets, like the exponent, the easier, like we can just neglect all the other ones because as you go along, it's just going to get closer and closer to 0.
Correct. It really makes things very interesting. Well,
Yeah.
but we'll end up with a very heavy question. I didn't want to keep it at the end, but I thought we'll keep it here so that it will summarize so many other things which we learned about. So, Amy, can you please read this question?
Yeah. Okay. Odd and even terms. So if O be the sum of odd terms and E be the sum of even terms in the expansion of x plus a to the power of n, prove that O squared minus E squared equals x squared minus a squared to the power of n.
And
And
also
part
this.
B,
Hmm.
4OE equals x plus a to the power of 2n minus x minus a to the power of 2n.
Correct. Now this is the end of our lesson right here, but at the end, very difficult question, but it is so important. I mean, it is going to answer so many other questions. We have looked into odd and even terms with the help of few examples. But here, I'll just summarize few things and leave the question for you. We'll upload this video. Then you go through the video. In fact, you can answer this question on your own later. Okay.
Yeah.
So if we are looking into the expansion of x plus a to the power of n, the binomial expansions will be nc0, nc1, nc2, and so on. And if you look into the expansion of x minus a to the power of n, alternating negative signs will appear.
Right.
Alternate. Now, the thing is, we have two sets always. We have two sets. So what we say here is, first term is odd. Do you understand? First term is odd, O for odd. NC0 is your first term in the series, correct?
Yeah.
1, 3, 5 is treated as odd numbers. So in the term numbers, they are odd numbers. And therefore, I can say NC0, NC2, and so on are my odd set of numbers, terms, and NC1, NC3, and all are my even set of terms, correct? As far as binomial coefficients are concerned. So we normally write them as O and E. So when I say odd, I mean all these. Do you understand? NC0,
So when you say
NC2, yeah.
when you say odd, you're saying R needs to be even.
Yes, odd needs to be even. Odd means yes. First is odd, right? First term is odd. First
Okay.
term is NC0, correct?
And that's 1, yeah, which is
One.
odd.
That is
Okay.
why. So it's very critical to remember this and understand it. And the even means second term is even, right?
Yeah.
R value is odd, correct? So that is how we separate them out. So we are looking
Okay.
at both these series, x plus a to the power of n and x minus a to the power of n as sum of odd and even terms and difference of odd and even terms. Do you see that?
Yeah.
Just think like this. And now, if I have to add them up, even cancels. I got 2 times odd terms.
Yeah.
If I subtract, then odd and odd cancels. I got 2 times even. You get the idea.
Yeah. Okay.
And a square minus b square is a plus b times a minus b. I can use that just by taking o minus e and o plus e.
Yeah. Okay.
The whole series has been now divided into just 2 letters, O and E. And with this O and E, we can do amazing things. And now you've understood the concept. You sit down and then work on it. how do we prove that O square minus E square is x square minus a square to the power of n, and 4 times OE is x plus a to the power of 2n minus x minus a to the power of 2n. So let this be an exercise for you, okay?
Okay. Yeah.
Perfect. So,
Where's my phone? Let me take a picture.
sure, sure.
Just okay. Oh. Okay. Yep.
Fine. Now, that's the end of our lesson. I mean, we have learned a lot of stuff today. Started things. Now, can you summarize what we have learned and what do you want to say about today's lesson?
Oh, it was very informative for starters. It kind of like carried on from last lesson, just like establishing all the different formulas and obviously new terms to me as well, and the rules. And today's lesson was more about the binomial theorem side of it and the expansion, and like useful tips and things that you could use in the exam. So yeah, so I definitely found when it came to like, you know, the approximate value question, when you split it into two, and we also did that in another question as well, just splitting the terms into two different things so that you can apply the binomial theorem method is like the key to unlock most of those tricky questions. So if you see like a question that looks really weird and it's like it's not in the right form for me to do it in, then put it into that form so you can do it. Also, when we came to that later on question where it had like so you had the like binomial thing, and then it said what is the number that gets into the form like minus 18 plus 144, things like that.
Polynomial
try and get it into the polynomial type, that's the one. Try and get it into the form so that you can match like that, let's say a kind of an expression nx or something to that number that they've been asked, and then just work through it like a normal algebra. That would work to find the constants in it. Then I also learned in reciprocal values, the even powers, they cancel out when the exponent is odd.
Correct.
So that's that. And I mean, there was obviously a lot, but I think what I'm going to do is go through the video once you upload it again, try and kind of create like a formula sheet of everything and just kind of memorize a few stuff, because I feel like obviously if I get that in my head, then I can apply it throughout, and as we progress through this, I would have some tips and things in my head, so that'll be good. Yeah.
So you actually highlighted the major points, and that's great. So look forward to your working with the exercise in your book, and if there is any difficulty, do let me know. And next lesson, as I was saying, we'll explore more about the binomial terms and the coefficients. We'll work more with the coefficients and those terms. I hope you find them very interesting. Okay then, bye for now, and all the best, Amy.
Thank you so much, sir. I really appreciate it.
Thank you. Bye.
Have a good rest of your day.
Thank you.
Thank you. Bye.